Okay, so the first question here, let's start with the first question. I'll just turn on my camera. Yeah. So the first and most important question that I'd like to ask, I'm not sure if you have already seen the contents for today's session, but let's go through that first. So are you aware what a loss function is? So you must have heard in ML that there is a loss function, or you must have heard about cost function, or you must have heard about objective function. So the first question would be, are you aware what a loss function is? You can just type yes or no. That's totally fine. I'll know how many people know, and I would know how many people don't know. So people who have just joined, that's the first part. What is a loss function? Or are you aware what a loss function is? Okay, so I'll tell you. So loss function, you must have heard about a loss function, or you must have heard people talking about a loss function. And when they talk about a loss function, so it could be a loss function. It could be interchangeably called a cost function, or it could be called as an objective function. Okay. So whenever people are talking about cost function, they are indirectly saying loss. Whenever they're saying objective function, so any of these three is one and the same thing. Okay. This is the first part. Now the second question is, that is totally fine. This is a loss function. Why would you define it? Why would you define a loss function in the first place? What is the loss function doing that you would even want to define it? Okay, so the point here is loss function is telling you something about how your model is working. Okay, and why would you define it? Because as soon as you're training the model, you would know, is the model training going in the right direction or not? So given a machine learning model, okay, now you have a model. Okay, now you're feeding in a lot of data. Fine. Now, while you're feeding in the data and the model is learning, you would need to know if the training. So I would just say this is the training process. Okay, we are training the model. So the entire training process, is it going in the right direction or not? That just for that, we would need the loss function first. And based on the loss function, even the model would know that it's not going in the right direction or it's going in the right direction. And based on that, it will try to optimize in a way that it goes to the final or most optimal solution. So that is the reason we would need a loss function. I hope that part is clear. How does it help? It helps because it helps the model tell, is it doing a good job or not? Okay. I hope this part is clear. So the goal. So for a loss function, what would be the goal? For a loss function, the goal, when we say this is a loss function, the goal is to minimize this. Okay. As soon as we try to minimize the loss function, we are making less mistakes. So last session, we actually saw that we had y final and we had y of model. And we had just defined a small function like this, and we were saying that this is the difference from the final and the final or the actual value and what is predicted by the model. And we want to minimize this. And this is what we are trying to do. So we are trying to minimize. So whatever loss function we get, we are trying to minimize that. I hope this part is clear. What is the goal? Why do we need a loss function? Okay. Now, you should always ask. So if you start learning, you should always ask why or what this term would mean. So now we know what a loss function is, but you should ask that why is it termed as a loss function? It could have been termed anything else, but why a loss function? It's termed as a loss function because it's giving a difference. So if you think about this, it's a difference. Okay. It's a difference between your predicted and the actual value. So it's giving you a loss, how much you have lost there. So it's a difference, and that is why it's called a loss function, just to remember. Okay. Also, if your loss is huge, it is actually telling that how much loss your business would incur. So that loss function is telling how much loss your business would incur if the model is not tuned properly or not trained properly. And these are the two ways you can remember why this function is known as a loss function. Okay, and it is a guiding function while we are training the model. I hope this part is clear. So now we know what a loss function is. I hope this is fine. So next part that I would want to cover is a data set. So this is a very simple thing, but it's not covered at a lot of places. So when we talk about a data set, you must be knowing what a data set is. And in the entire series of session, whenever we are talking about a data set, we would imagine it in a way that data set, we have X, these are the different features that we have. Last time I was only working with X1 or X2 because this is the second part. Let's have it till Xn. And we have the label. So this is the label. We don't always have the label. This is a supervised algorithm or supervised scenario that I'm talking about. We'll cover that as well. Just to keep it simple, let's have the label right now. And these are the features or signals. So in machine learning, features are also called as signals. So these are the features or signals that we have. Okay. So whenever we are talking about the data set, this is the data set that we have. And this data set could be huge. It could be small, it could be huge. So it could be maybe 1,000 tuples. And whenever I say tuple, so in the entire session, whenever I am talking about a tuple, this row, this one single row, this is a tuple. Okay. So it could be a set of 1,000 tuples, or it could be a set of 1 million tuples, depending on how much data you have. Now, it's a very fundamental question. How should you split the data set in a way that you can train the model as well as you have some data left so that you can even try to check your model's performance on the unseen data set? Now, my first question is, do we need the unseen data set or not? You can just type yes or no. And that shouldn't take much time. Just type yes or no. So I'll know that you know or you consider that we should have unseen data set or we shouldn't have unseen data set. So if we talk about that, I'll just wait for maybe 5 seconds. Okay. So when we talk about data set, we have different parts of it. Okay. There could be an unseen part, and the seen part is the part of the data which we have already feed it to the model. So model has already seen it. And there could be one part that's the unseen part. Now the fundamental question is, how would you split the data set? This is very important. Okay. How would you split the data set? This we already know that we would want a training part. A training part is mandatory. This is to train your model. Okay. The second part you must be aware of, that is the test part. That usually you split the data into train and test, and you perform your experiments, and then you check which model is doing good or which model is doing bad. But there is a different third type of split as well. I'm not sure, are you aware of it or not? It could be a development set. Okay. Also known as dev set. Or this same development set, people also call it as a cross validation set. So something on those lines. Fine. Now we have three different splits. Now train split, we know why do we need a train split? This is for training the model. Test, we know that this is for actual testing, the final performance. Test final performance. Okay. Why would we need this set? This is the development set or the cross validation set. Okay. Why would we need this? Now this is very important. If you're training a model, okay, if you're training a model, now there are so many hyperparameters of the model that you can tune. Okay. Now, based on those hyperparameters, the model might result into different performance, or model might be slightly different and giving you different results. So if you have multiple models out of the same one, okay, M1, M2, M3, and so on, let's say MK, okay, and I can just say MK. So you have multiple models. How do you check which of these models are performing good or not. Okay. So what you can do is, this is where you can use the dev set. What you can do is, you can just use a dev set and check the performance of these models. Whichever model is working best on this dev set, you can select that. So let's suppose M3 was working best. And this best model, this eventually you would be using the test set to run the test and check the performance. Okay. Now your question would be, a lot of places what we do, we don't have the dev set, we directly do it on the train set. We do it on the test set. That is totally fine. But the thing is, test set should ideally be used only for your final model. Okay. And because of that, we can say that we have the train set and we have a dev set, so that we can do all the model ablations with these. And the final model that beats all the other models should be tested on the test set. I hope this part is clear. Okay, now we know that we would want to split in a way that we have three different distinctions. Now, a major point would be, given a data set, how should you split it? In which ratio should you split it? So if I have given you a data set, okay, we can split it in 70-30. We can split it in 70-30, or we can split it in 80-20, or it could be 60-20-20. This is when you have the dev and test separate. Okay, so this is how you split it. Now my question is this the only way to split your data? And I would want you to answer this, because this is how I would know that you understand how to even split the data set. See, machine learning model training, understanding the model, that is all there. But first is the data set. You should know that how to use the data set very effectively, so that while you're training a model, even while you're testing the model, you have utilized the data very effectively. So is this the only way that you should split, or is there could be a better way to split? That is the first question. You can answer it on the chat. I'm just monitoring the chat. And don't worry, even if your answer is wrong, that's totally fine. At least you will know where you're wrong, or at least I will know what you're thinking, so that I can correct you there itself. Okay. So if you are still in doubt, so this split, we can have multiple other splits as well. Okay. That's the first point. Now, when would you have a 70-30 split, 80-20 or something like this? When you have a very small data set, right? If you have a very small data set, let's suppose we have only 1,000 tuples. Okay, we have only 1,000 tuples. If you have only 1,000 tuples, then a split like this makes sense, because in the testing set itself, you would need substantial number of samples, so that when you test it, your precision and recall numbers are good enough to say my model is performing good or bad. Okay. But in a case where your data set is 1 million tuples, would you still consider a 70-30 split? I don't think so. You don't need that huge 30% of your data in a 1 million data set for test split. In that case, what you can do is you can split it in a way 98% for training, 1% for dev, and 1% for test. This could be one of the possibility. And if you don't want a dev set, you could actually split it into 99% in train and 1% in test. Okay. There's one more thing here. If you're training a deep learning model, then it is advised. So if you have a substantial amount of data, it is advised to have majority chunk in your train, because you must be aware that deep learning models are models in a way that need huge amount of data to train themselves, because they have a lot of hyperparameters, plus they have to train. So I'm not talking about deep learning as of now, because we have not touched it, but there are a lot of edges, there are a lot of nodes there, and you have to optimize the weights there. So if there are so many parameters in the model, you would need a huge amount of data to train the model. And that is the reason in these cases, deep learning, when you're training deep learning models, it's advised to have a large chunk or large portion of your data in training set. Okay. I hope this part is clear. Got it. Okay. Now, if this is clear, there is always a tug of war between data. So if suppose you are, let's suppose you are creating an application, and like last time I told you that whenever I talk about an application in the entire course, I would be talking about a very simple application. So let's talk about a very simple application like a binary classifier of a cat or a dog. Okay. So what would it do? It would, given a picture, it would just say if it's a cat or a dog. I hope this part is clear. Now the issue is that while your app is telling, so you have developed a mobile application, and based on the image, you are just classifying it as a cat or a dog. The images that are taken by the user could be from the mobile camera. Okay. So that means your end result is the test set. So the test set is from mobile images. Okay. Let's keep it short so that I can write it. Okay. So these are mobile images. So now your test set is defined as mobile images. But just because you were training a model and you wanted more data, more training data, because you didn't have a lot of mobile images, you took a majority chunk of images from web. So you had mobile image plus web image. You considered these both as your training set. Because you wanted more data, you have also considered these web images so that your training set is huge for your training. And for testing, you only have mobile images. Do you see any problem here? You can just reply yes or no. Do you see any problem when we are having train set slightly different than the test set? There is a fundamental problem here. Yeah, it's better to just a second. It's better way to split. I didn't understand your point. Could you just slightly expand that? Okay, let me just clarify this. Okay, what is the fundamental problem in this case is your training set has some images, or maybe it could be a huge set of images that is very different from your test set. That means your distribution has changed. And you might feel as a human, because we don't see, if we see web images, if we see mobile images, we can easily identify if it's a cat or a dog. But fundamentally, the image has changed. Okay. So now let's talk in terms of the model, what the model is actually looking at. So what the model is looking at, the train set is like this. This is a train set. But your test set is completely different because these are mobile images. Okay. And this is where the problem begins. You can train the model as you can train the model in the most optimal way. Even then, you will not get results. Why? Because the distribution of your train set and test set is different. And as soon as your distribution is different, your model can do maybe a 99% accurate. It can be a 99% accurate model based on your training data. But as soon as you test it on your test data, it will not be that accurate because the distribution is different. And that's why it's a thumb rule that whenever you're trying to use the model, always have a dev set in a way that has the same distribution as your test set. So now you know why the dev set is very important. So you train it on any data set. Okay. Now, based on that, you have the dev set and your test set. Okay. Try to have this from the same distribution. Because as soon as you have this from the same distribution, while development itself, while you will be checking the model, you will know if your model is performing good or not. And if it's performing good on the dev set, it will automatically perform good on the test set because it's from the same distribution. If it's from the different distribution, then even if you're performing very good here, you might not be performing very good in the test set. So if you're, I'm just giving an example, if you have 99% precision here, it might be maybe 80, or it might drop to 60. It could be something like this on the test set. So that's why it's very important to check the distribution of your data. It's not always just pick out a data set and start training. You need to check the distribution of the data. That's very important. Okay. If this point is clear, let's continue. I hope this part is clear. Now we have seen two fundamental aspects. One is the data set aspect that we have seen till now, and other is the loss function. Now, the next, which is very important in terms of that you should know this by heart, I would say. It's a bias and variance, and you must have heard the term bias variance trade-off. Okay. So let's say bias variance, and you must have heard bias variance trade-off. You must have heard it. If you have encountered this before, it is very important to know what bias actually is, what variance actually is, what is the trade-off here exactly, and what you need to think about while you are training the model or while you are fine-tuning a model. Okay. So first of all, let's talk about what bias is. So to know what bias is, and I always, so I mentioned in the last session as well, while explaining any of the concepts, I'll always use geometrical interpretation because that's much easier. Okay, so let's think in terms of a graph. Okay, now if this is the graph, and let's keep it very simple, let's make a binary classifier itself. Okay, so let's make it like this. So this is one class. Blue represents one class. Okay, this is fine. Now 0 represents some other class. I hope this is fine. Okay. If this is the case, and what I would do or what I would like to do is I'll just quickly check if I have the tool. Yeah, I do have it. Let's keep the same example for for all the use cases that we have. Okay, so that it's much easier to use and much easier to use for yourself as well as. Okay, I'm just copying it below so that we'll use the same example. Yeah, all right. So this is the example, and let's suppose you are training your model, okay, and you train a model like this. Got it? Now this is a very simple model that we've already discussed last time. Now this is a simple line, okay. What is this line doing? Given the data, now you can visualize it. Given the data, this line is making an assumption that this is whatever your points are, I would pass from this intercept and I would have a certain slope. This is M. Slope is M. Okay. This is a bias, a very high bias model because it's not checking the data at all. It is just saying that whatever your data is, the line would still try to predict in the same manner. So what I mean by that is this particular data, if I'm trying to predict 1 or 0, so wherever the line is, it's just trying to say in a way. So it's not checking if it's classifying these values properly or not. So if I just change my pen, these ones are properly on one segment. This is fine. But this is an issue. This simple model is not even checking that. Also, it made another error. That's this one. So it correctly marked these points, but it made an error. And in future, if there are multiple points here, it is always making an error because it is not checking the distribution of the data properly. It is making an underlying assumption, and because of that, it's underfitting the data. Now I've added a lot of terms here. So as soon as you say that it's high bias, right? You are underfitting. What do you mean by underfitting? Underfitting is when your model is not trying to understand the data well and having a high bias in a way that it's trying to predict values without even identifying the data properly. So that is where you're underfitting the data. How can you actually try to mitigate this problem? That we'll discuss, but I hope this part is clear. So this is high bias problem. Okay. What will happen in this case is that even if you train, post training, your testing performance, so your performance of the model would be very poor because there's a high bias. So if suppose tomorrow you ask this model that is it a zero class or one class, it's just using a very simple or a line. It is just trying to say if it's above this line, it's a one. If it's below this line, it's zero. It's not checking anything else. Okay, so the performance would be very poor. I hope high bias part is clear. If you have any doubts, you can stop me right now. Otherwise, I'll just jump to high variance part. Okay, I hope that is clear. Now we have already seen a simple model. Let's see a model that is complex enough to understand your data very well. Okay, so for that model, let's see, this is the model. And this is your decision boundary of the model. Okay, I hope you know what a decision boundary is. When you're training a machine learning model, it creates a decision boundary around all the data points that you are using for training. So that's the decision boundary. Now, what is the problem with this model? The problem here is it has identified the ones correctly and it has identified the zeros outside ones correctly. But the problem is it is trying to understand the data very well. The problem would be as soon as the data distribution changes, or because this is the training data, as soon as the data slightly changes, because this model is fit on the data so perfectly that it will try to make errors. Not try to make, it will definitely make errors while you're testing it finally. So what is the problem with this model is this model is way too complex. This model should be slightly simpler in a way to identify patterns in the data rather than identifying the data or remembering the data. Okay, so this is the problem. So we have already covered the first problem. That is, I'll just change my. That is the high bias problem. This is the high variance problem. Okay, what is the problem here? High variance. I hope this part is clear. And this is an overfitting. You are understanding the data way too good, or you are understanding the data in a way that you're remembering the data. You're not trying to identify the patterns in the data, you're just remembering the data. And this is overfitting. Okay, learning too well is also bad. It should be generalized learning so that you identify the patterns and not remember the data. Similar case, the performance would be bad. Most probably it would be bad. Okay, so now the point is, you know what high bias is, you know what high variance is. Okay, now while training or while getting a model, you need to have a balance between this. Now getting a balance we'll definitely talk about later, because in the foundation course, let's just understand the terms. But while getting the balance, you need to understand that as soon as you try to change one of the aspect, that is bias or variance, the other might slightly drift, okay, or slightly move. So that is why there's a trade-off. That what are you more focused on? Do you want a more generalized model, or do you want a more specialized or more complex model? And that is the entire trade-off, that what you want at that particular moment, that's bias variance trade-off. Okay, I hope this part is clear. Now, if you have understood this, I would need some answers from you for these questions. And this is very important so that I know that whatever I'm saying is clear and you know. So if I'm saying that there is an error on my training set, okay. So in the training set, the error is around 1%. Okay. And let's suppose in my dev set, okay, in my dev set, my error is around 15%. What do you mean by this? Is this a high bias problem? Is it a high variance problem? What is it? That's the question. I'll wait for 5 seconds because this is important. You can just write it in the chat box. Given that your train set error is 1% and your dev set error is 15%, what kind of problem is this? And till the time you answer, I will write the next question so that you have time to think. Even if you're wrong, that's totally fine. We just want to understand, or that do you really know what a high bias mean or a high variance mean? Okay. And let's say dev. And for the second, let's make it very simple. 13% error, and this is 15% error. Okay. Any guesses for the first question? Okay. If there are no guesses, I would think that you know the answer. So let's solve it. So if we say this is error in train and it's a very small error, okay, that means your performance on the model on the training set, it's really good. Okay. But your performance on the dev set is bad. Okay. Error is high. That means it's bad. So if you compare 1 and 5%, it's bad. What does this mean? That on the training set, the model did very perfectly. But on the dev set, it was not able to match. That means it's trying to remember the training data. It remembered the training data so well that on the training set, the performance was really good. But as soon as it was tested on a data set which it hasn't seen, it made a lot of mistakes. And this is what we discussed is a high variance problem. So this is high variance. So as soon as you get to know that while you're training the model training error is very less, but while testing it's high. What kind of problem it is? It's a high variance problem. How do you solve it? That we'll see. But you should know what kind of problem you're facing at that moment of time. Okay. The second question is, when your error in training is 13% and your error in dev is 15%. So is it good? First question. Because these are very close by. So is it good that now it's comparable? So the point is, the goal is to have the least error. Okay. So this is also bad. Now these are comparable. That's a different story, but this is also bad. What is happening here is in the training set itself, the model is not able to perform. And as soon as you know that while training the model performance was bad, that makes it a high bias problem. That model is not understanding anything. It is just trying to predict things based on a very simple model. Okay, so this is a high bias problem. I hope this is clear. This is very important. I would emphasize on that. If you are going for any interview, any internship interview, any full-time interview, they will definitely ask you this. And if you get stuck here, that shows that you don't understand the fundamentals. So this is very important. And it's very important to understand it in a way that even if people twist the question, if they change the error rate, if they're trying to say underfitting, overfitting, you should be able to understand what they're exactly asking and tell them what you really know. Okay, so this is very important. Yeah. So now if this is clear, I actually had few more questions, but based on the interest of time, let's cover one more. Let's cover one more so that you know that it's not only one aspect, it could be multiple aspect as well. Okay. So let's suppose I will say error in train and error in train. Okay, let's make it 13 again. Okay, make it higher. And let's suppose we say error in dev. And this time let's make it double. So let's make it 30. What is the problem here? If you want to answer, you can just post your comments on the chat box. What is the problem here? What is the fundamental problem here? Now the problem here is that these are not comparable. That's the first thing. These are not comparable. This is 13, that is 30. There's a huge difference between these two. Second thing, on the on the trained data set itself, our model is not performing. That means it's a high bias problem. Okay, but the def set, on the def set, the error is much higher than your train set. That means it is also a high variance problem. So it could be possible that your model is suffering from both at the same time. This is very important to know. Okay. And because we have covered this, let's cover the other variation as well, because what's the point of not covering it if we are understanding it? Okay. So let's have the def set, and let's say I mentioned 13 and 30. So let's make it 0.5% and let's make it 1%. Okay. What kind of problem is this? That's the question. If you want to answer, you can answer. So now the point here is that on the train set, you are making very less mistakes. That means you are performing good on the train set. Okay. This is fine. I hope this is fine. Okay. But while performing good on the train set, you are also performing good on the def set. This is the main thing. And these are comparable. Okay. So you are performing good in both the places. That is on your train set as well as on your def set. This is low bias and low variance because you're performing good on your train as well as on your def. So you can have both high bias and high variance at the same time, as well as you can see you can have something like low bias and low variance at the same time. And this is what we would want. So given a data set or given a scenario, this should be your goal. Okay. I hope this part is clear. If this part is clear, considering the time, I actually wanted to cover, I had planned around 7 to 8 topics more, but considering the time, let's finish this topic thoroughly. And to finish this topic thoroughly, we should understand how to mitigate these issues. Okay. So this is the flow chart. I would say that you should remember this by heart. I'm not asking you to remember it, but you should understand it so well that as soon as you see that your model is suffering from a high bias problem or a high variance problem, there should be some next steps that you should have in your mind. Okay. So let's suppose you have a high bias problem. Now the point is, when do we have a high bias problem? We have a high bias problem when our model is very simple, that we have already seen. As soon this is the high bias problem, right? Our model was very simple. And because of the simplicity of the model, we were having a high bias problem. To mitigate this, the first thing would be make model complex. The entire problem was because it was simple. So to mitigate this, make it complex. That is the first thing. Second thing is, it might be possible that your training process, in the entire training process, your model wasn't able to find your optimal mapping function. Okay. That could be possible. And that is why the performance is poor. So what we can do is we can train for a longer period. We can train longer. We can give more time to the model to check the entire search space and find the most optimal point. Okay. This is what you would do if you have high bias problem. I hope this part is clear. Now let's see if you have high variance problem. Okay. So this is the high variance problem. Now, when do we have a high variance problem? When you are overfitting the data. This is the high variance problem. That your model is way too complex. You are overfitting the data. So to mitigate this, you can make the model simple as simple as possible. Make model simple. So the point would be, how do you make your model simple? There are multiple ways. One of the way could be regularization. I wanted to cover this today, but I don't think so. We have time to cover it. So let's not write it. I'll just tell you. I'll cover it and then we'll discuss it. But to make the model simple, and one of the techniques to make our model simpler is regularization. Okay. That's the first thing that you would do. Second, what you can do is it is trying to. So what your model is doing, it's trying to remember all your training data. What you can do is you can add more training data so that add more, okay, I'll just say add more training data so that it is not able to remember. So if you have very less data, it can remember everything. Okay. As soon as you have 1 or 2 million tuples, model may not be able to remember everything. And then it will start to try to identify different patterns. Okay. So what you can do is make the model simple and add more training data. And this is how you mitigate. So you should remember this as soon as you get high bias problem, you should think of something like this. As soon as you get a high variance problem, you should think something in these two lines. So make the model simple or add more training data. I hope this part is clear. Any doubts till now? Yeah. So this would cover this session. It's around 7 now. So this should cover this session. But if you have any doubts till this point, you can let me know and I can clarify that.